Hello, welcome to video number 5 of this series on discrete calculus. This is the final video where we look at the summation by parts formula, inspired by integration by parts. And so we're in discrete calculus, and my name is Nakia. Happy to help you through this journey. Let's go ahead and get started. What we have here is the formula for summation by parts. We're going to derive it first, and then we're going to use it. Okay, so we have two sequences, one called U sub n, the other one V sub n. Okay, and we're going to start with the product rule. This was given earlier in an earlier video. Not proved or anything, but we just wrote down the four major properties of the forward difference. This is one of them. The forward difference on a product can be written as this sum. It looks like you're doing them one at a time, but there's a strange n plus 1 there on the first one, but that's it. That's the formula for the product rule with forward difference. All right, so then we take those terms where they're at, we throw summations on it, sum the left and we sum the right. On the right, we break it into two different sums, and then we subtract over one of them. Okay, let's subtract over the one that has the forward difference on U sub n. And so what we're looking at then is the formula for summation by parts. Okay, we'll do some rearranging here. The first one doesn't even have a summation on it. It was if you have the summation of the forward difference, the fundamental theorem just says, well, you're going to plug in the last number plus 1 and subtract what you get by plugging in the first number. So using the fundamental theorem of discrete calculus on that first one, we then finally arrive at the formula for summation by parts. So there'll be two terms multiplied together. They're sequences themselves, and it's going to be up to you to be able to look at one of them and recognize it as the forward difference of another sequence, and then we can execute the formula. The other piece that's left over, it needs to be something that you can take the forward difference of without too much trouble. All right, let's see it used in two examples. Example number 1, we're going to multiply n times 2 to the n. We're going to do that from 0 up to k. All right. So the first thing we see a n and a 2 to the n. 2 to the n we can recognize for sure, knowing that the forward difference on it is itself, and we won't have any trouble at all taking the forward difference of n. So my two terms are going to be U sub n equal to n and V sub n equal to 2 to the n. We got the formula for summation by parts, and so we're going to first have the term where the product of u and v are there, but the fundamental theorem of calculus is used, discrete calculus is used on that, where we take and plug in k plus 1 and then we plug in 0. We rewrite that second term as the forward difference on the n, u sub n, and that'll be multiplied by the v but sub n plus 1. So 2 to the n plus 1. And forward difference on n. And thankfully the forward difference on n is equal to 1. And so we arrive at this point. Put in k plus 1, you put in 0, of course you get 0. Replace the forward difference on n with a 1. And now we have basically started with the sum of n times 2 to the n. And now we're with the sum of just 2 to the n. Officially 2 to the n plus 1, which we could definitely break down as 2 to the n times 2. And then we could recognize 2 to the n as the forward difference on 2 to the n. Use the fundamental theorem of discrete calculus one more time. Plug in a k plus 1. Plug in a 0 and subtract. Be careful with the 2's. We arrive at this formula. And I see 2 to the k plus 1 in both of the terms. So we should probably factor that out. So for these two terms, we have a k plus 1, 2 to the k plus 1, and then a 2 to the k plus 1 with a 2. Okay, great. We're going to factor out that. The last term doesn't have any 2 to the k plus 1s in it. It's just minus 2 times a minus 1, so a positive 2. And so what's going to happen there then is we take out the 2 to the k plus 1 for the first term. It leaves us with a k plus 1. Second term, it leaves us with a negative 2. And k plus 1 minus 2 is really just k minus 1. And so that'll be our formula for the sum n equals 0 up to k, n times 2 to the n. Depending on what k is, we'll have k minus 1 times 2 to the k plus 1, and then we'll have to add 2. We're going to use this in the next example. So we're summation by parts, recognizing the product, and dealing with the forward difference on the parts. Okay, example number 1. All right, now example number 2 looks exactly the same, except for we've gone from n to a n falling 2. And instead of k, we have a 7. So we could literally write out 7, 6, 5, 4, 3, 2, 1. We could write them all out, right? But no, there's a better way. Our better way is using falling differences. Okay, so we have 2 terms. 2 to the n, of course, is going to be the forward difference on 2 to the n. And n falling 2, we can take the forward difference of without too much trouble. So one term you could recognize as a forward difference of something. The other term you have no trouble really taking the forward difference of. The u sub n is the term that you can quickly take the forward difference of. The v sub n is the one you recognize as the falling, as the forward difference of some other term. And so let's now go execute the summation by parts formula. When it comes to the summation that we get in turn, it'll have us doing the forward difference on n to the falling 2, which is n, which is 2n falling 1, which is just going to be 2n. The forward difference on n falling 2 is just 2n. Okay, great. So we have the u and v. We're going to multiply those together and then plug in the 8. It's not a 7 we're plugging in. It's an 8 we're plugging in, k plus 1, and then plug in the lower limit of 1. So we have n equals 1 and n equals 8 are going to go in there. And then we have the forward difference on n falling 2 multiplied by v sub n plus 1. So that's 2 to the n plus 1, like before. And so what that does for us, 8 falling 2 times 2 to the 8, 1 falling 2 times 2 to the 1. We're going to do the 2 to the n times the 2 and factor out those 2 2's. And we arrive at a familiar sum. 8 falling 2 is 8 times 7. 8 times 7 times 2 to the 8. Don't worry about trying to multiply 2 to the 8 out. Leave it. 1 falling 2 is a 0, so that product is a 0. And then we're going to arrive at this place where we were at in the last example. And we have a formula for this that we derived. With k equals 7, it's going to be 6 times 2 to the 8 plus 2. Oh, there's a 4 on there, though. So we can put that 4 in. The 2 to the 8 and the 2 to the 3 for 8, we're going to call that 2 to the 11. See, without the calculator, it's kind of tough. And so what we're going to do is factor out as many powers of 2 as we can. And that'll make our life a little easier. And so rewriting 4 as 2 squared, we see that we have 11 powers of 2 in the second term as well. And so we're going to factor out that 2 to the 11. From the first term, we're left with a 7. From the middle term, we're left with a minus 3. And then the 2 to the 2 multiplied by the plus 2 there, that's just going to be a 2 to the 3. It's going to be added on 8 afterwards. And what's 7 minus 3 is a 4, who is 2 squared. And so that's another 2 powers of 2. 2 to the 13, take away 8, which is a good answer. But let's go ahead and get what it is. 8,184. All right. So thanks so much for watching this series. All in all, probably about 50 minutes, about a little under 10 minutes for each video. Hopefully you found it useful. Introduction to discrete calculus. We can go on from here looking at recurrence relations. This is dedicated to the group of students sitting outside my hallway, outside my office in the hallway waiting to take their quiz, asking if I could help them make some video, understand this topic of discrete calculus. And this video set is dedicated to them and all students that are learning this. Hopefully get something out of it. My name's Nakia. You can find me at CalcCoach.com. Please comment down below, like, subscribe, and I'll see you in the next video. All right, take care.